So we see so far the approach to optimize the SVM with some kind of formulation that was solvable with quadratic programming, but there are other ways to solve the same problem, but with different optimization approach. And for instance, we are looking at some formulation to do gradient descent over SVM. So with SVM, you know, we can restate the SVM as being a linear discriminant with an hinge loss function. Like we saw last week, we saw different linear discriminant with different loss functions, perceptron, least square, and so on. Now we can get into something similar to what we saw so far on SVM on the idea of maximizing the margin, but using this as a new criterion, so which is called the hinge loss. So the hinge loss is basically to compute the maximum value between 1 minus YT R, and YT is basically H. So it's basically the H times R. So 1 minus this and 0. So it means that we are looking at the fact that whether or not we are correctly classifying the data. So if the data is correctly classified and not in the margin, this thing is greater than 1. And as such, we will just, I would say, not saturate, but kind of having a floor value of 0. So we will not get a value less than 0. So this max over 0 is a way just to disable and get the loss at 0 for the properly classified instances not in the margin. For the samples in the margin, we will get a value of 1, you know, the 1 minus YT RT is between 0 and 1. So we got this value that is a loss. So we have a small loss for being correctly classified in the margin. And for the other, when we are misclassifying a sample, this value goes higher than 1. And so we have this thing we want to minimize, basically the loss state that we want to correctly classify all samples, and we want even to get correctly classified outside the margin, which is defined as this thing here. So we are penalizing the data on the right side, so the data that are correctly classified by the model, but in the margin. So these are the cases where XTRT is less than 1. So in fact, we should see that each criterion made a different trade-off on the nature of the error. So we have the 0-1 loss, the quadratic error, the cross entropy. So these are different things that we see so far. And the hinge is another one that is making a different trade-off. And so here we see what is corresponding, in fact, to YT RT. This is what we saw before. And so we see here the hinge. The hinge is the blue one. So we see that it is going lower and lower. And at 1, it is 0. So this is giving us an error value that is 0 for what correctly classified on the right side of the margin. But everything on the left here, it has some loss that is increasing as far as we go from that target of having a data well classified outside the margin. We can compare this to the 0-1 loss, which is basically a loss of 1 when we are making a misclassification, and the loss is 0 elsewhere. So it means that if we have one data that is correctly classified, but really, really close to the frontier, the loss is 0 here. While with the hinge, we have a signal in that zone that, you know, it is correctly classified, but still not right, completely right. We want to get some margin. And so we will push this data to be outside the margin. Compared to the square here, the square is the least square criterion of regression. We can see that it is doing a right job on the left side. So this is correct to get that shape. We want this to be close at 0. What is not that good is what is going on the right side. This is where we know we will put some emphasis on getting data that are super well classified here, having a big error. So we want to get them in that way so that we'll get the model to do stuff that are not totally correct. And as such, you know, if we go back to the discriminant in the space generated by a kernel, you know, we can follow on that formulation. So we have a function h here, which is stated that way. So we are using the SVM formulation with the kernel. So we are summing over all training sets, so what you call the XS here, with alpha S or S times kernel between XS and the X that we want to classify plus W0. So with this, what can we do? we can define that we will this time learn it differently. We want to learn the parameters alpha and W0 using gradient descent instead of using quadratic programming as we are used to do in basic SVM, standard SVM. So we will apply corrections to the hyperparameters. So we will make a gradient descent over the alpha t and a gradient descent over the W0. So minus learning rate, partial derivative of the error function according to alpha t here or according to W0. So basically it's the same thing that we saw last week on gradient descent, but instead of doing gradient descent on the W's, we are doing gradient descent on the alpha. And when we are developing this, we get into this, well, the updates will be done that way. We basically state that alpha t will be updated by one step in that direction. But we are dealing with a special case, you know, when we see that the correction will get us to a negative alpha, which is not supported because this is in our constraint. We cannot get negative alphas. Otherwise, it will not make sense in terms of the formulation. We just stop the value at 0. We don't go below 0. So the update is modified that way. Otherwise, for the constant, which can be negative, you know, it's the usual thing. We are just applying an update according to the gradient times and minus eta learning rate. And if we go back to the hinge loss formulation, we had this hinge loss before. So the error for the hinge loss corresponds to that thing. So we know the max that we had before is replaced by splitting the data between the correctly classified out of the margin and the one in the margin. So our set big Y here correspond to the set of data in our data set such that RT times H of xt is less than 1. So this is the case of data in the margin. So if RT H of xt is between 0 and 1, it is correctly classified in the margin. If it is negative, it is misclassified. So we are getting all these data, those who are misclassified and those who are in the margin. We are building up that set Y. And that set Y is used in our sum. So we are summing all the data that are in that case, and we are using this thing that was what we have in the hinge loss formulation. So we have 1 minus RT H of xt. But we are also adding that thing here. We are adding some kind of regularization. So we want to regularize that model to be sure that the alphas are as close as possible to 0. So this is really a Tikhonov regularization, a way to push the alphas to be as low as possible. We don't want all data to be supervectors. And with that formulation, we are maximizing the geometric margin because this is really about the geometric margin in the kernel space. And so we are working in the kernel space. This is the right thing also. And the value of R, so we'll see the kernel formulation later on, but the value here are R times H xt are between 0 and 1 are correctly classified, but in the margin. And we need some regularization. That's why we have these things here. And what we see is that the alpha, in fact, will explode because one possible way to solve that problem is to get huge alphas. And that may be a solution for getting this to be correct, but that is not a good solution overall. So we need to control the alphas. In fact, we need to regularize them. And the value of lambda here need to be adjusted empirically. There are no good values. So some kind of grid search over this lambda here and the sigma of the kernel is required. So, we cannot get rid of that. And in fact, just to be sure, we are dealing with the kernel formulation. Just forgot to say that in fact our H here is the H that we are defined before with according to the alpha t, RT, and kernel applied on XTX. So basically we are dealing with the kernel formulation of a SVM optimized with gradient descent using the hinge loss.